Om die enorme geld- en informatiestromen in goede banen te leiden, is een betrouwbare en geavanceerde infrastructuur nodig. En die wordt in de lucht gehouden door een organisatie die achter de schermen zijn werk doet. Belastingdienst Directie Informatievoorziening. Of kortweg IV.
Good afternoon and welcome to the second day of JSpring Digital. My name is Erwin de Gier and I am your host for today. And yesterday I really enjoyed the talks and I'm really looking forward to the talks for today as well, as we have two awesome speakers. We also had very good discussions in our chat yesterday. And if you haven't yet, please join us on Discord. It can be found next to the live stream. For each speaker we have a channel set up, so you can ask your questions during the talk and I will ask the speaker the question right after the talk, or you can engage in some further discussion with other participants and the speakers as well. And of course I have to thank our sponsors for making JSpring possible. They can also be found on our chat, and please visit their channels because they have really interesting stuff going on. I saw some 3D printing, there is even an escape room. So it's really an interactive conference, even though it's digital. And now let's welcome our first speaker, Urs Peter, and he will talk about concurrency with Kotlin coroutines.
Welcome everyone. About my talk about Kotlin coroutines, as beautifully announced. In the next 45 till 60 minutes, we are going to try to find answers for the following two questions. First of all, what are coroutines? And not less important, what are they good for? And with regard to the title of the presentation, what makes them so mind-rocking? Before we jump right away to coroutines, we will do a little detour so that you can make sure that we are on the same page, that we have the same foundation to build upon. So we go step by step and we start out with a very straightforward programming sample. I assume actually all of you can read and understand, even if your Kotlin knowledge is not very strong. So what we have here, we have some remote service call, which yields us a random avatar, which underneath does some blocking service call with, for instance, the REST template of Spring Boot you might be familiar with. Second, we have some save method where we save this particular user into a database, again using GDBC, which is a blocking driver, and returning the ID of the inserted user. Then we apply this logic, we fetch this random avatar, we save the user, we print out the details we're interested in. So this is easy, right? I assume really all of you consider this easy. And it does its job. It works fine. There's no additional fuss involved. It's okay, right? So you might be tempted to think, okay, why should I ever need something else? That's indeed a tempting possibility. Okay. What's going on? Okay. We have some wake-up call here. What does it say? This programming model has had its day. Okay, interesting. Didn't expect that. So why has this programming model has its day? It says, take a look at how this code performs under load. Okay, let's do that. I've prepared a little project where the calls you just saw are put into some endpoint based on the Spring Boot framework. And if you're familiar with Spring Boot or familiar with REST, which I assume most of you are, you should quite easily read what's going on here. Make it a bit more advanced. We check here whether this avatar URL is null. In case it is, we fetch a random one, otherwise we use the ones already provided. Then we have some blocking DAO, which saves the user using some GPA. And in the end, GDBC. This all, of course, is transactional, and our boss is happy because we fulfilled the business logic we need to fulfill. Okay, so let's see how this code performs. First of all, I need to make an additional hint. This blocking service is foreseen with a delay. So whenever we call it, we get an artificial delay of about 300 milliseconds, as you can see here. So a call will not take shorter than 300 milliseconds, that's for sure. Let's see if this is correct. I do the call, and we see it takes about 300 milliseconds. That's correct. So 300 milliseconds is the delay, and 22 is for the rest, the parsing, the storage to the database. So it's more times, and you see it's never beneath 300. All fine and dandy, right? Let's go one step further. Let's do a performance test. What I have here is some very simple command line tool to do some performance testing. And what it does is we have here 100 concurrent users, which do a total of 200 requests, calling this endpoint to insert the user. Okay, let's hit the button and see what happens. It's spinning, it's spinning, it's spinning. So what do we see? The minimum amount of time we had is 305, which is explainable because we have this delay. But when we look at the median, so the 50% of our users, it takes 1 second. So 3 times longer than it took, as long as it could took, which is 300 plus milliseconds. And look at the max, 8 seconds. Horrible. Why is that? Let's try to find an explanation. So let's look at our architecture. What we have here is our application, and we have some thread pool in this application. Whenever a request comes in, a thread will take it out from the pool and will be associated with this request. Then the thread, in this case, does the remote network call, which is blocking IO. So the thread will be blocked until it gets a reply. Once it gets a reply, it does the call to the database, which will block again. And once the database responds, transaction will be committed, all in the same thread, and the response will be returned. So what happens if, for instance, this remote web service is slow? Could also be the database, could be any resource which is not within the application, or we get heavy load. What happens then is that our thread pool will be exhausted quite quickly, which causes no new requests to be served because we have no thread available. So the requests will block here until a new thread becomes available, fetch the thread, and then process it. Which of course doesn't our users make very happy, because as we see, a particular user in the performance test we just did had to wait 8 seconds, which is unacceptable in 2020, right? In addition to that, all tasks are executed sequentially. So parallelism cannot be leveraged. For now, we don't really need parallelism, but we'll see later on that it can come in very handy in many scenarios. So we can say that the sequential blocking programming is easy. I agree. It is straightforward. It depicts our business intent clearly. But it is not performing on the load. It wastes resources. And by doing so, it also contributes to global warming when it wastes resources. So to exaggerate a little, of course, it screws the planet a bit. Or just to say it in more formal words, it doesn't perform on the load and it wastes resources. So this problem of this piece of code is not new in that sense. Some years ago, they realized that we need to do something about it. And they came up with a solution. And this was the solution. Excuse me. Reactive programming. Yesterday we had a beautiful talk about the reactive manifesto. And the question is, was this really to the rescue? Did this solve our problems? Also here we go step by step. This is the example revisited, but then made reactive by using the Spring facilities for that of project Reactor. And for now, I do not go into the details. We will look at the details further on. You see, it's a bit more code. There's some new abstractions introduced. There is some flat mapping map. So there's some new stuff going on here. But first of all, I would like to know how this code performs. And again, I have my project here. So this was our blocking example here on top. And this would be the reactive sample below. A bit more complicated than what you just saw, because we still need to do this null check. And then we cannot just relay to our variables. We need to wrap them in some sort of mono. Then we can do a remote call. And then here we do, again, the flat mapping and save. So let's see if how this reactor user one performs. First, we do it on a single request. So reactor / user example1. And as you can see, it's about as fast as the blocking sample on the left as a single call. It's 300 milliseconds plus some overhead. Let's do the performance test. With the exact same parameters as before, so 100 concurrent users. We do a total of 200 requests calling this particular endpoint. Let's hit the button and see what happens. Whoa, look at this. This looks considerably better than on the left side, right? So the min is still about the same, but the median, look average. So 50% of our users get a response in 4 milliseconds. I think that's perfectly acceptable. And look at the max, 500 milliseconds, still acceptable. So the worst case user here waits half a second, which is fine, and not 8 seconds, which is, calculate the factor yourself, 30 times more than it could take. How is this possible? How does reactive programming do that? We have more or less the same application architecture again, but now, and this is the kind of funny thing about it, is our thread pool has even less threads than the thread pool we had before. Normally, by default, you get 1 thread per core. So if you had a quad core machine, then you would get 4 threads. And not more, that's all. So when a request comes in, again, of course, we need a thread to do the execution, and all requests are executed asynchronously. When a thread hits an I/O boundary, then it doesn't block. All our communication is non-blocking, meaning that it kind of offloads it, probably registering some callback, what needs to happen once we get a response, and goes back to the pool to take on new work. So actually, these threads are continuously spinning. They are never, ever blocking, never, ever waiting for something. Eventually, we get a reply from the web service, then a new thread will be associated with it, do the network call for the database. Again, hit the I/O boundary, says, okay, there is some blocking involved. I go back to the pool, which is the callback. And then eventually another thread. It could, by the way, also be always the same thread. We don't know by that. So there are 4 and just one of these 4. Another thread that is ready for work will pick up the response and return the reply. And by doing it with this approach, we get this tremendous boost in performance. Beautiful, right? So also, when we look at some alternative scenarios, so say this remote web service gets slow, or we get some heavy load, now we still can accept new requests because nothing blocks. There will be threads continuously spinning. Of course, at a certain point in time, everything blows, but it will be longer than before. And on average, we can process really way faster than with the blocking architecture. In addition to that, and that's the beauty of this model, we can also leverage parallelism. We haven't done it yet, we will see it in a minute, but we can quite easily. So in the end, our customers will be happy with this type of architecture. There is some important remark to make. First of all, whenever you do some remote service call, HTTP or some other protocol, you will need an async IO client, an IO client that is based on the new IO of Java. In our example, we use Reactor's web client, but there are really many more available. I've seen almost all HTTP clients you have right now have some async way of doing their thing. When it comes to the database, things get a bit less fancy, I have to confess. So first of all, we cannot really use GDBC. We could, by the way, but this is more hassle to set up because GDBC is blocking inherently. So we have to rely on a reactive driver, an async driver. And in this case, we used a R2DBC. That's the counterpart of GDBC, the reactive counterpart, which for most popular databases are available, like, as you can see here, Postgres, MySQL, Microsoft SQL Server, H2. But if you're burdened with Oracle, sorry, and Oracle doesn't support it and also does not plan to support it. Then you would have to find another solution. And they are, but it's more custom, more complex to set up. So it won't work out of the box. Okay, so let's revisit this example. Instead of actually depicting what's really relevant for this code, we all of a sudden get some new abstraction weaved in our code. And that's evident because we have to rely on libraries. It's no language feature, right? Reactive is no languages, it's a library. And whenever we use a library, we have to stick to the language feature we have. And in this case, it's just object methods and so on. So we get this new abstraction. And the problem with this abstraction is that it's very invasive. It's kind of viral. Once you start out with this mono thing, you will have it all through your code base. So what is a mono, by the way? A mono is a construct that will yield eventually a value or an exception. Eventually means that somewhere in time. Can be right away, can take long. It is very comparable to a completable future if you know these constructs, actually almost the same, except for the fact that a mono is truly lazy, whereas completable futures can be eager for the details. Okay, so this is our construct. And in order to fiddle around with this construct, to do our business logic, we all of a sudden get these combinators, flat map. Maybe by now you're not very shocked anymore about flat map, but still there are many combinators to learn. So the first big disadvantage we have with this piece of code is that our business intent gets really lost. This is a very simple example. Real business examples are considerably more complex, way more conditions, way more error handling that has to take place. And even with this simple example, there are quite some combinators involved. And yeah, kind of removing our clear view on what is happening here business-wise with this code. We have to, with our mind, eliminate all these flat map to see what is actually happening here. And the second, which is about as severe in my opinion, is that this stuff is really hard to learn. I consider reactive programming as a specialism. If we now were not digital, we would be in a room, I would ask you, who is using reactive programming on a daily basis? I would ask that. I can't, sorry, we do it next year when we can come together again. And of course, I can only guess, but in my experience, also other colleagues I talk, not many are using as a default. Maybe they have some special problem they solve, but not as a default. Because it's hard to learn. Besides that, once you understand how Reactor works, then it's not a given that you know how RxJava works or Akka streams. These are, again, kind of new worlds you have to dive in to know what is going on and how they work. So, do we have a real answer for this problem? And of course, you guess already where I'm heading to. That's quite evident, I assume. Yes, I think we have. And the answer is called coroutines. So let's look at the code we saw previously, but then from perspective of a coroutine. But of course, first of all, it would be nice to introduce coroutines. What is a coroutine? How does it work? Coroutines are the core building blocks of Kotlin concurrency. And the beautiful thing about them is that you can express logic sequentially, as you're used to from your blocking sequential programming, and implementation, so to say, the compiler generates code which figures out all this asynchronous. So the example we just had before with coroutines looks as follows. So we have these very same methods, no additional abstraction involved. Of course, we have this fancy keyword here. In a minute, we will see what this means. This is how I would call this piece of code. You simply say random avatar, avatar URL, save the user, directly accessing the value without to have to fiddle with another abstraction which allow you to do this asynchronous program. So if you would show this piece of code to your boss, I'm really sure he understands it. And whenever a boss understands code, then I think it's really straightforward. Okay. Of course, we have these suspend, we have this launch. There is some stuff involved with it. And in this presentation, I will try to give you a good overview of what you will encounter to get started with coroutines. It's not much, but it's still something. Before that, let's do a little step back and see at the architecture of coroutines and how are they related, for instance, to threads. You can look at coroutines like very lightweight threads. As you might know, every operating system has processes. And there were, in the early ages, there were also even web platforms that used a process to handle a single request, which of course didn't perform at all when they got a little bit low, because there are really not many of them. When you look at threads, there can be considerably more threads, but they are quite heavy in terms of memory usage. So one thread consumes about 4,000. 1 gigabyte of memory allows you to create about 4,000 threads. Now let's look at coroutines. 1 gigabyte of memory, and you can create 2.4 million of coroutines, which is a factor of about 600. Impressive, right? With the very same model, so the very same GVM. Okay, so let's compare the two, how we create them. This is simple example how we create a thread in Kotlin. Kotlin has these neat helper methods, so we can say thread, and this does the thread dot start with a runnable dot run. Just all this fuss is gone in Kotlin. You just capture the essence. We create a thread, we sleep for a second, and then after 1 second, statement. This, of course, will be printed right away because this thread still sleeps. And important detail, we have to join the outer thread because otherwise our program would exit right away. I guess such an example you've seen before. When we look at the coroutine counterpart, it looks as follows. So first of all, you cannot create coroutines with a constructor like we could create threads. That's not possible. You always have to rely on a builder method. And the builder method we use here is run blocking. And this run blocking kind of bridges the world between threads and coroutines. And because the word blocking is involved, it implies that you probably shouldn't use it in production code. Second, we have another builder which launches a coroutine. So within here, semantically the same like in the thread, a coroutine is launched, and then comes the beautiful thing. Now, our coroutine doesn't sleep in a blocking fashion, but it suspends. So this means it kind of pauses itself. Then after a second, some scheduling will take place, and it will wake up and proceed. So what's the difference between the two? These are the more or less exact same snippet we saw before, but now we do many of them. So we create here 1 million of threads, we create here 1 million of coroutines, and then execute the code you just saw before. And of course, with such examples, it's always known to have a real proof how this really works. I have this code here. This is the thread example. This is the coroutine example. I'll also print every 1,000 times how many threads or coroutines I've created. Okay, then let's run the thing. Ooh, it's already terminated. So what you see is that after 4,000 threads, the thing stops because out of memory, and that's not surprising because I use 1 GB of memory, and we just saw before that 4,000 threads fit in 1 GB more or less. So our code just knocks off quite quickly. As you might expect with the Coroutine example, it's a whole different story. As you can see, in almost no time, 1 million Coroutines are created. Now they all sleep or delayed for 5 seconds, and then they start printing out all their dots until everything is done as expected. So, as a summary, using threads, you crash your GVM quite fast. Using coroutines, it's just really easy peasy, piece of cake. Okay, so let's dive a little bit deeper and look at all these fancy keywords we saw: suspend, launch, and so on. Suspend is a very crucial construct. It's at the heart of coroutines. And what it does is that it allows to such a function to be paused and resumed at a later time. And when this happens, this resume or pausing is done by the implementation of Kotlin, not something you have to care about. So they are really like normal functions, but they have some additional capability that they can be paused and resumed. These functions, because they have this special capability, cannot be called from any piece of code. So first of all, if you had some normal method, you cannot call a suspend method. Like our main method, delay would not work. You have to call a suspend method from a coroutine. Here we just launched one. Then we call delay on it. This would work. Or you could call a suspend method from another suspend. This also works. If you see what the compiler does with suspend methods, I think it can get of evident on a conceptual level how this more or less works. What does the compiler do? The compiler does the following. The compiler compiles an additional parameter in this method, which is a continuation, so to say, a callback interface. This is what the compiler generates. And as you might know, with actually all async constructs, you will need some sort of callback. So once we get a response from a network layer in async fashion, we need this callback thing to proceed, to know what needs to be done with the answer. So this is actually the base for all kind of async program. Of course, we've created a lot of abstraction about it, but this is the same with coroutines. They still rely on actually traditional callbacks. So this is how the continuation looks like. And there are two important methods. It's resume with a value or resume with an exception. Remember what I told you about monos? They will yield eventually a value or exception. It's conceptually actually the same. Eventually, we get this coroutine be resumed with a value or be resumed with an exception. But here it's built into the language. It's no library, it's built into the language. We also have to look at those builders. And actually, what we really have to consider are the properties associated with these builders, because then we can get a good overview of the core tools that are needed to make coroutines run as they should. So these are 4 of the most important builders. We have things with scopes. We'll discuss scopes in a minute. So we have run blocking, launch, and this async. So now let's look at how their signature looks like. The first object, which is very important when it comes to coroutine, is the coroutine context. And as the name implies, we have some context to make a coroutine spin the way it should. And one of the most important parts of this context is the dispatcher. As you might know, a GVM only knows about threads. A GVM doesn't know about coroutines, really not, at least not yet. There are some projects which are trying to do that, but in the near future, definitely not. Only thread. So also coroutine will be executed by thread. So we need to provide some thread pool that will eventually make sure that the coroutine is executed. And in coroutine terms, this will be a dispatcher. By default, you get the default thread pool, which, as we saw in previous examples, has as many threads as we have cores in our machine. The second one is a bit more complex, but it's a beauty, really. So first of all, we have this fancy function literal as receiver. That's a Kotlin concept, which is a bit interesting, especially when you're new to Kotlin. It's even suspended. This might look a bit fancy, but we'll see in a minute how this works out, how it's used. Then it gets more clear. What does the coroutine scope do? What it does is it coordinates the completion of many different scopes. You can have parent scope, nested scopes, child scopes, even way more considerable amount of nested scopes. And all their completions is managed by this scoping. And this is beautiful because then you as a programmer do not have to do synchronization manually, which is quite hard when you look at threads. And this handling, so this coordination of different completion of scopes is called, has gotten a term, which is in the meantime quite popular, which is called structured concurrency. Let's look at an example. So this is the example we saw before, more or less. When we call this run blocking, right, we have this fancy function literal with receiver. And what this does is that it provides us right away, without having to assign a lambda parameter, with the receiver, so the first argument of the function, which is a coroutine scope. So we get right away access to the coroutine scope. The coroutine scope is this. So when we then call launch, we do not call launch on a top level method, but we call launch on this particular coroutine scope. And because it's the first scope we created, it's the parent scope. Then, because we launch another one, we get another coroutine scope. Launch is also here. So we get then a child scope. And then we do our delay. And what's the big deal about that? Why am I telling this? Have you wondered why we have in the thread here join, and here we have no join? That's exactly what scoping does. So what happens here is that run blocking will right away print out started, because this will be delayed and executed right away. But it will not proceed because the parent scope knows that, hey, there's still some child scope not completed yet. So I have to wait till this child code has completed, and then I can continue my program. Whereas in the example of threads, you have to do the joining all yourself. And this is really very, very convenient, as we'll also see in later examples. So this is structured concurrency in action. So then let's dive into some live coding. And make some more, hopefully, illustrative examples. And I assume that, first of all, you might be interested how this first example we saw looks like with coroutines. We've seen the bit in the slides, but I think it's worthwhile to do it just to get on the same page. It's a one-liner, actually. So we can say user repository dot save. Then we have this user. We have this avatar URL. In case it's not there, we call our avatar service, which returns as a random avatar dot URL. And now you see that my ID is not really happy, because it says suspend function save should be called only from a coroutine or another suspend functions. Okay, so do I have to create a coroutine myself, or no? It's really simple. You just let your ID do the job, and you turn this particular function into suspend. And that's the beauty about Spring Reactor and the support for Kotlin. They just figure out all this building with coroutine scopes and so on. So for you, you just start right away with suspend function, and all the rest is taken care of. So this is really a low threshold to step in. And then, of course, we also want to know that this performs as well as our reactive sample, right? Just to be really sure. Let's clear stuff. So this was our reactive sample we saw before. Let's see if our new sample performs as well. So here we have then our final user sample, user 1. It takes again a single call 300 milliseconds. That's the same, right? Let's do the performance test. And as you can see, it performs as well as the sample before. So actually almost the same. Which, as we see later on, is really not surprising because also coroutines under the hood will use Reactor. And the magic that is involved with that will also be shown in a minute. Okay, so let's make this business scenario a bit more complex. What we want to add now is some sort of email verification. So we have this enrollment service where you can verify an email. And in case the email is not valid, I want to throw an exception. With Reactor, again, it's quite hard to write this business logic. It's not intuitive because now I cannot say if email valid, then no, I have to go flat mapping because I have to stay in this monospace. And then I have this variable which eventually comes available. And then here I have to do the if statement. If not valid, then throw illegal argument exception. Invalid email. No, this is not going to work because once you're dealing with monos, you always deal with monos. So we also have to wrap our exception into some mono error. Then we can do our else, and the else is more or less the same logic as we've seen before here. Our avatar thing. We say return, and we finally created our service. So let's see how this performs. As you might assume, it should take longer because I think I'm calling the wrong endpoint here, users 2. Probably the email verification is still a bit flawed. That's correct. Sorry about that. So this is live debugging during a presentation. Wonderful. Okay. Now we get the right call. So we actually expect this same service to also have a delay of 300 milliseconds. So we verify email. If it's correct, 300 milliseconds has passed. Then we do the avatar, which again 300 milliseconds. And all in all, it should take more than 600 milliseconds. And we call the service. And this is what we do right away. First time GVM needs to heat up. So as you can see, it's 600 plus milliseconds. So let's rewrite this in Kotlin. We have to check whether this email is valid. So we have, again, this enrollment service, verify email. And this is the beauty about Kotlin coroutines, that we simply can stick to our well-known exceptions. Now we can say throw legal argument exception, because they're fully integrated with coroutines. So when you have the scoping thing, also even exception handling is integrated as if it's a native normal blocking exception handling feature. So if we throw and else, we return the one-liner we programmed here above. And as you can see, we again get some complaints because we haven't turned our method into suspend method, but once we've done that, everything is fine and dandy. Okay. Right now, we haven't really looked at what happens if we would like to leverage parallelism. In order to do that, we would have to rely on the async builder. As you might see, the signature is more or less the same as we've seen before, but the return time is a bit different. We get a deferred back. What is deferred? It's quite a simple construct. It has a single method that is relevant, which is await. And what does await do? So here we have the more or less same example as before. We create here some rabbit async, and then in our print line statement, we call await. And again, await is suspend method, so it does not block. So here, what happens is the code will execute and will hit a suspension point here because this coroutine, this child scope, is not yet completed. So it will wait for completion. Once completed, it will print the statement and proceed, making asynchronous programming and asynchronous constructs very easy to use. So I will show you how this looks like in Reactor. More or less done the example already. What you get here are two monos. And now you need to kind of combine the results of two monos. And then again, you have to look at how these combinators look like. In this case, we need to use zip. Then we can get two values of two monos at the same time. So once both have yielded value, this function will be called avatar email, and then we can do our save action. In the coroutine example, there's a little bit more involved than normal. So first of all, we need a coroutine scope. So what this does, it gives us access to the coroutine scope of a suspend method. This is a helper method offered by the coroutine scope. Because in many cases we don't use it. Here we do, because we need to have this async builder, which has to rely on the scope, and we can kind of get the scope out. Then we simply can more or less copy this code. So we have our valid email. And what we do now is we do not throw an exception anymore. So the business requirements have changed. We do not throw an exception. We simply save that this user has a valid or an invalid email address. Okay. Then we have our avatar URL. And then we can save our user repository dot save email valid and our avatar URL. So this was the example before. This is not yet async. This is still synchronous in that sense. It's the individual calls are executed asynchronously, but the logic, because of the structured concurrency, will execute sequentially. So first I will have valid, then I will have avatar, and then I will have this call. So this will take, if all these calls take 300 milliseconds, 600 milliseconds. But now we want to have async, right? So what we can do is then use here the async keyword. Then we get back a deferred. And now we have to call here await. So that the code will hit suspension point here, and until both awaits are resolved, save will take place. And as you can see now with this approach, that will be the final method. It will take about 300 milliseconds again, even so we are calling two backends, which both of them take 300 milliseconds each. Beautiful, right? Okay, we've seen that in the Reactor, there is a perfect integration with coroutines. But how about other reactive libraries like Completable Futures, RxJava, and so on? So to round up our presentation, let's take a look how the interoperability between different kind of asynchronous reactive frameworks can quite easily be achieved. So with coroutines. We have a lot of glue code available for coroutines, and they look more or less like as follows. So here we would have our reactive library we would have to call from our Kotlin code, which will return a mono. We cannot change that. What we then could do is we could call this mono and then have some extension methods, which I call await me. I intentionally chose a name which is a bit silly, that you see that you can do this yourself. Of course, all these libraries offer this for you, but you could also quite easily do it yourself. So this await me, what does it do? It will not block, of course. You also have a .block method on mono, but please never ever use this, especially in production code, because then your performance will deteriorate very quickly. So await me will not block the thread, it will suspend it. And actually all major reactive libraries have such a gluing code available to lift their abstractions into coroutines. How does it work? Quite simple. So here I create my extension method. So I say every mono gets an await me method if I import it. Then what we also can do, we can get a handle to our continuation. Before we got a handle to our coroutine scope, but you also can have a helper method to get a handle to the continuation. Once you have the continuation, we can do the gluing. So here we subscribe. So subscribe is on the mono, this.subscribe. And then we do a normal reactive subscription. And once a value is available, on next, and the subscriber completes, it will be set. So the continuation will be resumed, or in case of an error, resume with error would be called. This, of course, is a simplified version. The real version is a bit more complex, but this perfectly works. If you would do this for futures, it's even simpler. And as I said, I've seen quite a lot of async libraries right now on the web, and they all provide some helper, some extension methods that lift their async construct into coroutines. So this brings me to my conclusion of my presentation. And because we have about 3 minutes left, I also would like to show you some simple snippet about testing, which actually kind of underlies my conclusion of my talk. If you would like to test your reactive code using Reactor, then you would have to learn another abstraction, which is the testing abstraction. So you get the step verifier, which then is on DSL, which allows you to test that this user has done what it's supposed to do. And really, especially beginnings, this is quite hard stuff. You just want to get this user out, but you're always dealing with this abstraction you're not really waiting for, but you will have to, because this is the price what you pay for normal reactive. This is the coroutine example. And the only thing we have to do is start a coroutine scope with run blocking, and then we just simply do our normal business code as if no additional abstraction would be involved. It's also quite nice debugging. So if I debug here, right away you can see the value of the user, whereas here, it's quite hard to debug. You can always do some blocking call to get the value out, but it's just not optimal. It takes considerably more time to test reactive code than if you just could rely on the essence of it without an additional abstraction involved. Okay. So my conclusion is that with coroutines, we really get the best of both worlds. We have async as a default. We can do parallel. We can leverage parallel programming. And of course, you need to know some basic constructs like the suspend, like these builders, and so on. But believe me, this is really not so hard to learn. Of course, there's a learning curve involved, but you learn it once and only once. So no matter which reactive stack you will use, if you go native coroutines or you use Reactor, which has all these lifting methods to lift them into coroutines, you only learn coroutines, and then you're all set. And readability of your code won't suffer. The only thing you probably see sometimes is suspend keyword, but for the rest, it's just capturing the essence of the business intent you want to express in your software. So I would say, yeah, if you want to become a reactive programmer, that's quite easily possible. with almost no effort. Okay, thank you for listening to my presentation. And maybe now I can take some questions.
Very interesting talk. I'm a big fan of Reactive myself, so I'm really looking forward to learning more about Coroutines. We have a lot of interesting questions, so I'll dive straight in. The first question is there a way to see whether an operation is a blocking or a non-blocking operation, maybe a keyword or a pattern? And do you have any tips for designing interfaces that can serve both blocking and non-blocking operations?
Yeah, that's indeed a very good question. And what I've done so far, there is no clear distinction between what is blocking and what is not blocking. This is not really particularly a problem for coroutines. That's also a problem for every reactive stack. Also in reactive, you could do blocking calls within a mono, and then you would have the exact same problem. And yeah, in coroutines, it's more or less same. So you have to know from that perspective what you're doing. So when you use a blocking library, then in the context of coroutines, you would have to provide a dispatcher which has way more threads than the amount of core threads you get. So that's a limitation which is not yet solved. So as said, not only coroutines, but actually in every async program library.
Yeah, so actually it's up to the developer to make sure you have a clear method names and a clear interface to make clear whether you're using blocking or non-blocking calls.
That's correct. And it's a bit evil because should you use a blocking library and somewhere build it in, your performance will really suffer extremely. And that's indeed a problem. Maybe, yeah, the community should address this to have some pattern or some annotation or to make sure that probably there are annotations available, I assume. I haven't used them, but they're probably available. But still, it's not really a safe way of doing that. Yeah.
Yeah, I think there's even a tool from one of the Spring guys. It's called Blockhound, and it can detect whether you're using blocking code in your application. It's very interesting.
Yeah, that would be a good one. Yeah.
And we also have some questions about Project Loom, of course, because it's the next big Java thing, very related to coroutines. So the question is, I think Oracle is putting their money on Loom using fibers for asynchronicity. So reactive programs, of course, can get complicated. You address this as well. And the person who asked the question says, in his experience, the same can hold for Kotlin. It can be easy to make mistakes, and advanced use cases of coroutines are still experimental functionality. So do you think it's worth to invest in going reactive now with either reactive programming or coroutines, or should we wait until fibers are available in Java?
Yeah, that's a good question indeed. Yeah, I just can give my personal answer about this. Project Loom is about 2 years old. We've tried it some months ago. We had to compile a GVM, so I didn't get a very solid feeling that they're very far with it. You could make some threads execute more or less like coroutines, so doing every operation asynchronously, but really no care was taken of how they would solve structured concurrency, how they do asynchronous programming. So in my opinion, Project Loom is really not yet production ready, far from. Whereas coroutines and also all the other active libraries, they are. There is a lot of blocks, a lot of information to find, a lot of projects using it already. So personally, I would not wait. No, I would use this stuff right away and not wait till hopefully Project Loom will deliver.
Yeah, so go for coroutines right away.
That would be, yeah, after this talk, I cannot say no, right?
Of course. And the final question, I like this one as well, because I think this is a point that a lot of people will run into. It's about transactions. So what happens with the transaction propagation when using async service calls? I assume the transaction won't be propagated when using asynchronous calls.
Yeah, that's also a very good question. And we just saw this transaction annotation, then you think, okay, this is just gonna happen and it's fine. But that's really true. It's just going to happen and it's fine. So in Reactor, they took great care to make this work. So what they do is they will hop their context from one thread to another. So whenever a thread offloads some requests, the context will be offloaded, and the next thread that picks it up, or it could be the same, of course, will take on the same context. So by doing that, they can ensure that the transaction context and also actually every other context, like security context and MDC context and so on, is propagated. The beautiful thing about coroutines is that we have this coroutine context. So coroutines are really designed to have context associated with them. Whereas in normal, or like in Reactor, you have the thread local and just have to hope that things are there. In coroutines, they have a beautiful handle to deal with context. When the code you saw, we still lived on what Reactor offers us, but should you have some sort of native coroutine library, then you can make this context way more explicit.
Okay. Well, thank you for your talk again and for answering the questions. If you have time, please hang around in our Discord chat, because I think there's more people ready for a discussion and to learn more about coroutines. We go for a 10-minute break and are back with the second talk.
Okay, thanks.